You already met several geometries in M203. Apart from the ordinary Euclidean geometry, you've met non-Euclidean geometry and projective geometry. But we've adopted a unified approach to all of these geometries right from the beginning of the course, when we considered Euclidean geometry as consisting of a space, the plane R2 in this case, plus a collection of allowed motions, the isometries, that preserve the essential properties of figures. Well, this unified approach is due to a 19th century mathematician called Felix Klein. He noticed that this collection formed a well-defined mathematical object. In fact, it formed a group of transformations. And using this idea, he was able, in fact, to achieve a unification of geometry by saying that any geometry, now not just R3, any geometry consisted of a space plus a group of transformations which preserve essential properties. Now, this not only gives us a unification of geometry, but it allows us to distinguish between geometries in a very simple way. So we can compare Euclidean to non-Euclidean and projective geometry using his idea. Well, let's start off by looking at non-Euclidean geometry.
Remember, when we studied non-Euclidean geometry, we had a different interpretation of distance, so that straight lines looked like arcs of circles. But we still had a group of transformations acting on a space. In this case, the space was a disk. Each transformation again preserves the essential properties of figures. For example, the angles haven't changed in this triangle, and angles are preserved by any of the transformations. Here's the image triangle of another one. Concentrate on its angles as we apply the inverse transformation. They don't change. In fact, also preserved is the non-Euclidean distance between points. So we can unify the two geometries in spirit by saying there's a space in each case, there's a group of transformations acting on that space in each case, and the groups preserve essential properties. In this case, the essential property of distance between points in the two different interpretations of distance. What distinguishes between these two geometries is the fact that the space is different and it's a different group of transformations that acts on it. Alan.
Well, okay, but what about projective geometry? Well, the same idea of preserving essential properties still applies. But now the essential properties don't include distance, because projective transformations don't preserve distance.
Well, remember that any projective transformation is just a sequence of perspectivities. Here's one that we had in the television program. You take a point in space and a plane. Then you peel off a copy of the plane and put it somewhere else. And a point in this plane is mapped by projecting through the fixed point down onto the codomain. So a figure like this, a circle and a line, gets mapped to one like this, an ellipse and a line. And you can see straight away that distance isn't preserved. You see, this diameter of the circle has been stretched into the major axis of that ellipse. And you can see also that ratios of distances aren't preserved because the centre of the circle here divides this diameter in two. But the image point down here doesn't divide the image line in two. So when we compare the properties preserved by projective transformations with those preserved by Euclidean transformations, this is what we get. Points map to points, lines map to lines, and a point lying on a line or incident with a line maps to a point on a line. But this time, distances aren't preserved, ratios of distances aren't preserved, and as a matter of fact, neither are angles. Well, it seems a pretty drastic step to cut down the properties being preserved to just these three, but nevertheless it still gives us a geometry because we still have a space and a group acting on the space. Now the group's very different from the Euclidean group of transformations because it preserves a different set of properties. And as a matter of fact, the space is different too, because if you remember, the projective plane isn't just the ordinary plane R2, it's R2 together with ideal points, points at infinity. And that's because there's a line of points here in the domain which get projected out parallel to the codomain. They have no image until we add the ideal points to the codomain. And similarly, there's a line of points here in the codomain which are projections along rays parallel to the domain. And these points are all images of the ideal points of the domain.
So that's the three geometries that we've met so far, and each of them exemplifies Klein's viewpoint because they consist of a space plus a group of transformations acting on the space. So if you change either the space or the group, then you've got a different geometry. And we've lots of geometries, but we've really only one subject called geometry, which we can consider as being the study of a space plus a group of transformations acting in the space. And that's Klein's very elegant point of view. Geometry is the study of a space plus a group of transformations, and if you give me such a group, you'll find that it will preserve certain essential properties and hence define a geometry. Conversely, if you have a space and certain essential properties you want to preserve, you'll find that all these transformations which preserve them do in fact form a group. So it's all very neat. Well, in this week's text, we actually discuss another geometry, affine geometry. Now, it turns out affine geometry is very useful because of the essential properties that it actually preserves. It turns out that in terms of these essential properties, affine geometry is intermediate between Euclidean and projective geometry. What do I mean? Well, it doesn't preserve angles and distance. On the other hand, it does preserve the ratios on a line, which projective geometry doesn't. Well, in this week's text, we discussed this algebraically, but now we want to give a geometric description.
First of all, the space for affine geometry is the usual Euclidean plane R2. But the transformations aren't just the usual Euclidean ones. In fact, to construct an affine transformation, you begin as if it's in projective geometry. You take a plane, a copy of the plane, which you put anywhere you like, but you don't map between this one, which we take as the domain, and this one, the codomain, by projecting through a point. Instead, you project along parallel rays, like this. Here's where we've put the codomain, and here's a copy of it, which is the domain. Points in the domain are mapped by projecting along these rays onto the codomain. So a configuration like these two black lines crossed by a white one is mapped into these three lines in the codomain. Now, in general, the angle between these directions and the planes are entirely arbitrary, and an affine transformation is made up as a sequence of such projections like this. Okay, what properties do they have? Affine transformations have the properties of sending points to points, lines to lines, and incidences preserved. So in that sense, they're like projective geometry. They have some properties else in common with projective transformations. Length, for instance, is not preserved. This length is copied into this greater length in the codomain, and angles aren't preserved either. This angle in the domain is mapped onto this smaller angle in the codomain. But they do have one property which distinguishes them from projective transformations. They preserve ratios along a line. Take, for instance, this length. It's equal to this one, and both are half this one. Those ratios are copied onto the codomain. This length is equal to this one, and both of them are half of this one. You can see why if I remove the front portions of each plane. You see, what happens is that this domain line, the rays of the projection through it, and the codomain line all turn out to lie in a plane. Now, because that's the case, and because these rays are parallel, they must cut the same ratio on the domain line that they cut on the codomain line. That result is called the intercept theorem, by the way. What's happening is that each segment is being stretched, but by the same amount. Now, that's true whatever line we take, although the expansion factor may be different. For example, this ratio here is repeated exactly in the codomain here, although the expansion factor is clearly different. But every affine transformation has the property that it preserves the ratios of lengths along each particular line.
Well, now that we have affine geometry, we can point out a very neat and important consequence of Klein's viewpoint. And we can do this in terms of the essential properties preserved by the transformation group. You see, if we look at these properties, we see that Euclidean group preserves more properties than the affine, which in turn preserves more properties than the projective. So there is a sense in which Euclidean geometry is less general than affine, which is less general than projective. In what sense? Well, we can make that sense more precise. It turns out that the Euclidean group is a subgroup of the affine group.
To see that, it's enough to show that the translations, rotations, and reflections, which between them generate the Euclidean group, can each be realized as affine transformations. The idea is quite simple. For a general affine transformation, your hands go anywhere you like, the planes, if you like, go anywhere you like. To get a Euclidean map, you keep the planes together. Suppose you want to realize a translation. You just slide the domain. This really is a translation. The points which were along my index finger have been translated so that they now are mapped onto my little finger. To get a rotation as an affine map, you just rotate the domain. To get a reflection as an affine map, you take the domain out, reflect it, and put it back in. So we can realize each of the Euclidean transformations as an affine transformation, and so the Euclidean group is a special subset of the group of affine transformations.
So in fact, the Euclidean group is a subgroup of the affine group. Well, actually, that's what you'd expect, because the Euclidean group preserves more properties than the affine group, and so the affine group must contain extra transformations which destroy these properties. And that just corresponds to Jeremy's hands being inclined at an angle, and for a Euclidean group, of course, the hands are together, superimposed, and so this preserves all of these properties. So, in effect, the affine group is a bigger group than the Euclidean group. Well, by the same reasoning, you'd expect the projective group to contain the affine group as a subgroup. Well, there's a bit of a problem here, you see, because the affine transformations just act on the plane, whereas the projective transformations act on the projective plane. That contains these ideal points. So we really can't say that yet. What we have to do is to extend the action of the affine transformations to the whole projective plane. We've got to say what the affine transformations do to the ideal points.
Remember, we think of ideal points in the projective plane as points at infinity in a certain direction. The ideal point, for instance, in the direction of these parallel lines in the domain plane is the point where those parallel lines all meet, point at infinity. Now, affine transformations have the enjoyable property of preserving parallels. These lines are parallel, so are their images in the codomain. So we make the obvious choice of image for that ideal point. We send the ideal point at infinity in the domain to the ideal point where the image parallel lines meet in the codomain. In this way, we extend the effect of every affine transformation so that it becomes a transformation of the projective plane. That's the easy part. The hard part is to show that the affine transformations form a subgroup of the projective group. To do that, we must show that every affine transformation can be realized as a perspectivity, that is, as a projection through a point, or perhaps as a sequence of perspectivities.
Well, here's a perfectly general parallel projection. I've just shown 3 points and their images. And I'm going to reconstruct that as a sequence of 2 perspectivities like this. Now, I've chosen an intermediate plane here, and this plane passes through the intersection of the domain and the codomain. And 2 points, x and x dash. First, we project through x to the intermediate plane, and then on through x dashed to the codomain. And I can choose x and x dashed in such a way that the sequence of two perspectivities reproduces our original parallel projection. Now, why is that possible? Well, the explanation requires several steps, and the first thing to notice is that the line x dash defines a line in space, and it meets the domain at a point A. Now, A is projected through x to the intermediate plane, and then straight on through x dash to the codomain. So A dashed is one of our original lines, so x and x dashed must both lie on one of our original rays. So that's one restriction. X and x dashed must both lie on one of the original parallel rays. And if they do, then one of the points in the domain is automatically mapped to its correct image in the codomain. But what about all the other points? How can we choose x and x dashed so that the other points of the domain map to their correct parallel images? Well, first of all, before we tackle that, let's think about the ideal points. You've already seen that an affine transformation sends ideal points to ideal points. So perhaps we could try and find x and x dashed so that points at infinity in the domain end up as points at infinity in the codomain. Well, now, a ray of projection from a point at infinity in the domain must be parallel to the domain. Otherwise, it would be a finite point. So I have to try and arrange that a parallel ray to the domain is followed by another parallel ray to the codomain. Well, the way I do this is as follows. I've left off the points C and C dash just to simplify the model, but I've added in two new planes. I chose x arbitrarily, and I drew a plane through x parallel to the domain. And that plane meets the intermediate plane here in a line. Through that line I drew another plane, but this time parallel to the codomain. And I chose x dashed to lie on this second plane. Now, the ray of projection from a point at infinity in the domain lies in this plane, passes through x, and hits this line. And then the following projection sends it still in this plane through x dashed out to a point at infinity in the codomain. So an ideal point maps to an ideal point. And it looks as if we're doing well. But have we done enough yet to ensure that all the other points in the domain map to their correct images? In other words, do we know yet that B dashed is parallel to A dashed? Well, in fact, we can show that because of the special way I've chosen this intermediate plane. The fact that it passes through the intersection of the domain and the codomain ensures that B dashed is indeed parallel to A dashed. Well, let me show you why that's true. I'm going to slice through the model with another plane. This time the plane will pass through the points A, B, and X. And because of the arrangement of points and lines, the same plane will also pass through the points A dashed, B dashed, and X dashed. Well, here I've sliced the model, and you can see that I've removed the top half. Well, now notice that this pair of black dotted lines are parallel. They're parallel because they're slices through parallel planes. And for the same reason, these white dotted lines are also parallel. They're slices through parallel planes. And I'm going to use these two pairs of parallel lines to prove that the line B dashed is parallel to A dashed. Well, let me start by putting on the plane of the cut. I've left off some of the lines to try and make it a little simpler, but I've added in the line B dashed. And I want to prove that that's parallel to the line A dashed. Well, look at the checkered triangle Q, B dashed. If I can show that the line A dashed divides these two sides in the same ratio, then by the converse of the intercept theorem which we had earlier, it will prove that AA dashed is parallel to BB dashed. And I can prove that using the intercept theorem twice, once on each of these pair of parallel lines. First of all, look at the line QB dashed, and look also at this black line, which, remember, is a slice of the intermediate plane. Well, because these dotted white lines are parallel, the ratio QX dashed over X dashed B dashed is the same by the intercept theorem as the ratio this length divided by this length. And now, of course, I can use exactly the same argument on the line QB. Because the two black dotted lines are parallel, by the intercept theorem, the ratio QX over XB is the same as the ratio this length divided by this length. In other words, the ratio QX over XB is the same as QX dashed over X dashed B dashed. So by the converse of the intercept theorem, AA dashed is parallel to BB dashed. And that's all we wanted to prove, because B is a perfectly general point of the domain, and we've shown that it maps along a ray parallel to AA dashed. So, you see, the way I chose my intermediate plane and the points X and X dashed has ensured that this perspectivity, followed by this one, reproduces the original parallel projection. Well, now let's have a purely visual summary of that rather complicated argument.
So indeed, an affine transformation can be obtained as a combination of perspectivities, as a projective transformation. So the affine group is indeed a subgroup of the projective group, a subgroup which preserves the line at infinity. Well, what have we achieved in this program? First of all, we've seen Klein's unification of geometry, where we regard geometry as being just the study of a space, together with a group of transformations acting in that space. And as a consequence, we've been able to capture the purely geometric idea of one geometry being more general than another in terms of the purely algebraic idea of one group being included in another group.